Welcome to Academic Digest class. So today I'll be teaching you electric dipole, dipole moments, and dipole moment of force. And you know that moment of force is also called torque, so I can call it dipole torque. Welcome to Academic Digest class. So first of all, you need to know that when you have a charge, let's say Q positive, and you have another charge Q negative, two charges separated by a distance. Let's say we'll call this distance, you know that this is half. Let's say we'll call this A, So let's say all together, or let me use R. So let's say all together 2R. So two charges, the product of charges and distance is what we call electric dipole. Or you say the combination of two equal but opposite charges is what you call dipole. It's just like when we did couple. If you remember, when we did moments, we said something about forces that are equal but opposite. So when we have two equal charges that are equal or opposite, you call it dipole. Now, what is dipole moment? Now, dipole moment, just as you know, so please look at this. This is the sentence saying that electric dipole is equals to, this is 2R, Q, then 2R. So any of the Q. So if I carry this one now, or you say it's this way, QR. And when you look at it, you see that this is now the sentence saying Q times Q. Like I don't have to, if I'm considering just this one, it's going to be QR. If I'm considering this one now, it's going to be QR as well. If you put it together, this plus this is becomes 2QR, or you say Q2R. That is electric dipole for you. So 2R, 2Q. So if I know this, when it now comes to electric dipole moments, so when it comes to electric dipole moments, first of all, we need to go and pull out what moment is. If you remember very well, we said that moment, once you hear moment is simply the product of distance and anything. So for example, if it's force I'm talking about, is the product of force and distance. If it's charge I'm talking about, is the product of distance and charge. If it's acceleration I'm talking about, is product of distance and acceleration, which you know you can't have moment of acceleration because acceleration is inside force. So but anytime you hear moment, is simply talking about the product of distance and physical quantities. So if I know that, let me now say that moments, dipole moment will simply be, electric dipole moment will simply be product of distance, and we say that the distance we have here is 2R. Remember what we are using here. So if we are using this illustration up here, it's going to be, okay, let me write it, product of electric force and distance. And we know that electric force is given by F equals to QE. Therefore, dipole moment, which is represented with P, will simply be equals to force, which is QE, times distance. And the distance we have here is 2R. Are you seeing it? So if we know that is R plus R, 2R. So that means that electric dipole moment is equals to QE 2R, or 2R QE, whichever one you want, whichever way you want to put it. Now for electric dipole torque, or electric dipole moment of force, is the same thing with this. The same thing. But the only thing is that if I'm considering this now, this is supposed to be electric dipole moment, or electric dipole moment of force, which is torque. So what I have here actually is supposed to be torque. That is T equals to this. But if I want to talk about electric dipole moments, I want to talk about electric dipole moments, that is P. sorry, P, this is torque, which we normally write as maybe something like this. So torque. So electric dipole moment now will simply be force and perpendicular distance. And notice that the perpendicular distance is simply maybe when I have R. So, and since what we are talking about is not moment of force, but rather moment, and we say that moment is simply the product of distance and anything, and the distance we have here is 2r. And then remember, we are talking about electric, so charge Q. So electric dipole moment, or moment, is simply Q2r. Q2r. But once you are talking about electric dipole moment of force, which we call torque, it is QE2r. So electric dipole moment is simply charge and distance. So if we know this, you can now know, you need to know that all these things we are putting up here is simply situations whereby I have maybe a charge here, Q plus, or maybe a charge this way, or maybe a situation where I have a charge this way and a charge negative this way. These are the cases that I'm talking about here, because in this case, y, this is y-axis, is at y-axis, and I told you that y is equals to sine theta. And notice that anything y is sine theta. Notice that anything x is cos theta, if you still remember when we are making angle with the horizontal. So if I know that the angle I have when something is up like this is 90 degrees and 270 degrees, which we know that sine 90 is equals to 1. Sine 270 is equals to minus 1. We have no business with 270 here, so we are using sine 90. Now, if I'm talking about this, the origin is 0. The origin here is 0. And this side is 180. So maybe let me do this, sine 270 equals to minus 1. So now notice something. Cos 0, if you notice, cos 0, because when something is at x, we said is cos. So x now will be equals to cos 0 is 1, is equals to 1, and x equals to cos 180 is equals to minus 1. So if I know that, that means that in these situations, if I put maybe that the charge is this way, you see that cos 0 will simply be 1, because by the time you do maybe using this now, and I come and do, because we can have all these things that I'm saying, we can have situation where this t is actually equal to, that is when it's at angle, an angle Q2r sine theta. So if it's at this, you notice that in my class I hate putting differentiation and integration, because it's not everybody that did further maths in secondary school. So but if you want to use that one, I'll still make a video on it. So you say once you integrate sine, you are getting once you differentiate sine, you are getting cos, and if you integrate cos, you should be getting negative sine. I believe so. Yeah, I'm correct. So if I know that I'm not doing that here, I'm not doing changing sign or changing cos here, what I'm doing is to put this to you so that you know that when it is at 90 degrees now, for this case now, let's say we have sine 90 here. You see that sine 90 is 1. 1 times everything here is the same thing I have here. So these cases that you see here, these cases I gave you are cases of 90 degrees and 0. So that if you now look at it very well, so if you now look at it very well, you now see that it is when maybe your sine is at 90, if you put it here is set. But there can be a situation where this charge is at an angle. Let's say I have this now to be Q positive and Q negative. So you can now see that this thing forms a vector. That is the summary of what I'm trying to say. It forms a vector. And if you remember when we do resolution of vector, it's either you are taking what is at z, because everything is supposed to be at x and y axis. So but when you are now taking it to x and y axis, you now pay attention to the fact that x is cos and y is sine. So if I'm going to be taking this now, let's say to x axis, or let me say to y-axis first. If I'm taking this to y-axis, the torque will now be the same as, yes, what is here is already here. So to y-axis. So torque to y-axis is what you have here. But when I now have torque to x-axis, torque to x-axis, you will now see that what I'm going to be having is simply T equals to QE 2R cos theta. And notice, this theta that we are saying is simply maybe when we are taking it that it is final. So we can have a situation whereby maybe we have this moving from one point to the other. It doesn't fall at exactly 90. It falls in between, maybe changing it from an angle to another. So I can have this to be T torque equals to QE 2R cos initial theta, that is theta 1, or theta 2 minus theta 1 cos theta 1. Good. Cos theta 1. Let me do it here. So torque can be QE 2R cos theta 2 minus cos theta 1. That is final minus initial. So if I know this, you will not need to know. I need to point out this because if you go to your textbook, you will see something like that where they normally tell you PE and all that. Notice that if you remember, there's something called potential energy, which is, we told you that mechanical energy is equals to potential energy plus kinetic energy, and each of them, whenever you have plus sign in between something, means that they are equal. So I can just choose to represent energy with PE or just KE. So if you remember that theory very well, it will simply mean that P is mgh, if you remember, and this mgh is force times distance. Remember that h is when you have a height, but normally when you don't have a height, that means that is distance because all of them are in meter length. So see that this is fs, and remember that torque talks about the same thing, which is force times distance. So if that be the case, it simply means that this torque that I'm seeing here, that is everything that I'm seeing here, QE, if you remember, QE is force, is it not? Force. And then notice that this is distance. So this is force and this is distance, is it not? So that is why you say that this is the same thing as saying potential. And notice something again, notice something. If I come here, potential energy, this thing that I have here, everything that I have here is the same thing as my potential energy. And if I know it, I can say if I have P now, this P is 2Q, is Q2R. Notice Q2R. I can call it P, my dipole moment. Now, if that is my dipole moment, I notice that this is electric field, which is E. I can now put it here, PE. So you need to know this. You need to know this, know how to put this. That is why they normally tell you that PE, what you have as PE is equals to QE2R, and this is what you have as your torque. So if I know this, I can simply say that anywhere I see QE2R, I can say that torque is equals to PE, potential energy, or you say dipole moment times electric field. They give you potential energy. So is times cos theta 2 minus cos theta 1. I know that the best way to learn something when it has to do with watching video is you going over the video over and over and over and over, listening to what I'm saying. When you do that, you see that it will be easy for you to understand because it's not hard. So very simple theory. So it's more like torque is the same thing as potential energy when you consider it in terms of this electric field that we're looking at. So cos theta 2 minus cos theta 1. So you need to be knowing this, which means that anytime I am taking this, now notice from simple harmonic motion, we said that simple harmonic motion, that potential energy is maximum here, because it is coming to rest fully. But here, over here, kinetic energy is maximum. If you still remember our class, that time, and we said that this middle part is the equilibrium. The video is on my channel, simple harmonic motion. So if I remember that, that means that anytime I am told that something starts from equilibrium, I will calculate something so you see it. But anytime I'm told that something starts from equilibrium, that I should find the angle, I should find the energy there. That means I'm looking at potential energy. if it starts from equilibrium, and at equilibrium I'll be considering x, and that is cos 0, and cos 0 we know that is 1, if you remember. So but if they tell me that something is at y-axis or at its equilibrium position, that is at its equilibrium position, and that is it is moving and is at its equilibrium position, that I should calculate the energy there, I can still use potential energy, or I use mainly kinetic energy, because at that point it is in full kinetic energy. Notice kinetic energy will run from this end maximum here at this peak then. So if that be the case, you need to know this. So this is the equilibrium position, if you remember. Equilibrium position. So at this equilibrium position, kinetic energy is maximum. Then from this point, the starting point, and this equilibrium position is the origin. Yes, like I can say I call this 0 if I'm looking at this. So notice from this point, this end is 0, this end is 180. So this is the equilibrium position. Okay, let me use EP, or somebody might mistake it now. So let's solve a question so that you get what I'm trying to say there. So if I know this, we look at this question. The question says a molecule has a dipole moment of about 4.3 times 10 raised to the power minus 30 coulombs meter. The two atoms are separated by about 2.0 times 10 raised to the power minus 7 meter. What maximum torque would this dipole experience in a 3.5 times 10 raised to the power 3 Newton per coulomb electric field? And how much energy would be required to rotate the molecule 45 degrees from its equilibrium position of minimum potential energy? So if they give you this kind of question, I will tell you that the best thing to do first is to write solution, and when you write this, the next thing is to make a sketch of what they are saying. That part where they normally explain that the positive force and the negative force will do this one, so first is cancel out. That is not, it's true for you to note that when you have equal charges, opposite charges, that the force is cancelled out. But when something is given to you, you need to put these things that I've explained in mind. That's why I did not bother putting that explanation here. So molecule has dipole moments. Remember I told you that dipole moments, another name for dipole moments, if you remember, dipole moments is P. Do you remember dipole moments P? So they gave it to me. P is equals to, always first write what you are giving out, then you make sketch. 4.3 times 10 raised to the power minus 30 coulomb meter. Then the two atoms are separated by about, the two are separated, yes, by about, they did not say, wait, separated, so from one end to the other end, so that is the distance, so distance r, or you say 2r. So if you put that 2r, you might confuse it, so just write distance for me, so you don't put yourself inside trouble, because you know that 2r I was using is simply talking about half of the distance, combine it together is 2r. So distance given is 2.0 times 10 raised to the power minus 7 meter. They now ask us, what is the maximum torque? Don't just write torque. The torque they are talking about is the maximum torque max. What is the maximum torque? And they said it's 3.5 times 10 raised to the power 3 Newton per coulomb. Okay, wait, they're asking me what is the maximum torque. Sorry. Then they now gave me electric field E, and they said it's 3.5 times 10 raised to the power 3 Newton per coulomb. That is the first question they're asking me. What is the maximum torque? Now, the second question they're asking, they said how much energy would be required to rotate the molecule 45 degrees from the equilibrium position, from its equilibrium position of minimum potential energy. That means that at that point, potential energy is at an angle. Yes, is at an angle of cos theta. Then they also gave us cos 45. So that means that we are going to be using this one now, the last one we got. So we are going to be having that for our torque, Okay, let's find our torque first. For our torque, to find our torque in this case is to simply say, they say what is the maximum torque? Torque is maximum. Okay, let's now draw this before we move to the first one. So the second one. So this is the first question. So if I have this to be my charges q plus q minus, then they gave me distance from this point to be 2.0 times 10 raised to power minus 7. Then they gave me p dipole moments, yes, q2r, yes, q times distance. So they gave me the dipole moments to be the dipole moments, and you remember that we said that this is force times distance. So they gave it to me. They did not give me what the charges are. They did not give me, but they said that dipole moment. So if that is the case, that means that the maximum torque will be maximum at this end, because you remember what torque is. If you remember when we normally explain this, when we have maximum torque, is simply the same thing as saying product of distance and perpendicular, product of force and perpendicular distance. So perpendicular distance to this will be this when it's at 90 degrees. So torque is maximum. Torque is maximum at 90 degrees. So torque is maximum at, my God, 90 degrees. So torque is maximum at 90 degrees. So if I know that, I want to say that means that T now will be the same as saying P E, and notice that 90 degrees is at y-axis and we use sine theta there. So P is sine 90 degrees, and sine 90 degrees is 1. So 1 times P is P. So this is going to be T equals to 4.3 times 10 raised to power minus 13 times 2. Yes. What am I doing? What is 2.0? 2.0 is distance now. No, times 3.5 PE. Yes. Yes, PE. That is the, if you remember from this equation. So since they gave us dipole moments and they gave us dipole moments, everything here, both charge and distance, they gave it to us to be 4.3 times 10 raised to power minus 30. Then the electric field, they gave it to us to be 3.5. So let's do the maths. So if we do it, we have 4.3 times, okay, times, yes, 3.5. So that I have torque to be 15.05 times 10 raised to power minus 30 plus 3. So I have T equals to 15.05 times 10 raised to power minus 27. So times 10 raised to power minus 30 times 10 raised to power 3. Okay, yes. So this is the answer we have. You can also write this as, this is also the same thing as saying 1.505 times 10 raised to power minus 26. Why did I write this? So that if you see this one in your calculator, you don't get confused. They just did all those our standard form and decimal points. They did decimal points, taking this to 1 decimal point. So this is your answer for the maximum torque. Remember, write it somewhere. I said torque is maximum at 90 degrees. If you remember, product of force and perpendicular distance. If you remember those days. So now let's move to the second part of this question. So the second part said how much energy would be required to rotate the molecule. So let's say that I have this molecule now. how much energy will be required to rotate the molecule 45 degrees from its equilibrium position of minimum potential energy. So if I have this and I want to move this down to this point 45 degrees, notice that I'm going towards x-axis, and remember we say towards the angle use cos, away from the angle use sine. So if I'm taking this now, this is the equilibrium position, is maximum. If I'm taking this now to x-axis, I'm having cos 45, and he said something from its equilibrium position of minimum potential energy. So, and that means that what we are using is simply this one, this. So this is what we are going to use. P dipole moment times E, then cos. Somebody will want to tell me, why didn't you use potential energy? Remember that he said that everything here is equal to potential energy if you check it. In as much as if you put it together, it's force times distance, and it's the same thing as saying dipole moment. When you put this Q2R and E, it gives you. So focus on the dipole moment and the angle. So the potential energy now they are talking about is you considering the fact that it is starting from equilibrium position, and at this equilibrium position they are saying that we should have, yes, remember, see, if you remember, at equilibrium position kinetic energy is at its maximum. If you remember, at equilibrium position kinetic energy is maximum and potential energy is at its lowest minimum. If you remember, while at this point now kinetic energy is lowest and potential energy is the most. So if that is the case, that means that there is potential energy at this point. So moving from here, potential energy will simply be lowest, and if it's lowest, that means you have cos 0 minus cos 45 degrees. So cos 0 minus cos 45 degrees, and cos 0 is 1, so minus. So you need to note that. So you need to note that. So this will now give me the sentence saying I'm moving from here, from this point. That means at this point the energy here, that is what we are checking. They said how much energy. So there is energy here. The energy here will simply be the energy I'm taking to move this from this point that it is the lowest. The energy here, kinetic energy, is maximum. Now that means kinetic energy here is for sine. Then for me taking this thing now to x-axis, the energy that I'm taking now is simply, as it is in its equilibrium, I'm taking it from cos 0 and then I'm moving it to cos 45 because I'm going towards x. So I will not consider this. Kinetic energy because I am leaving this. I'm moving towards the x-axis, that is taking it to 45 degrees. Whichever way I'm taking this now, if it's this way or this way, I'm going towards x-axis. So I'll be considering the fact that at this point it is going to be moving from cos 0, that is the energy is moving from cos 0 equilibrium and then going to 45 degrees energy. So it is going to be the second part. Now the energy there will simply be E equals to energy, that is potential energy, equals to how much energy. So the energy, let me use the energy will simply be equals to potential energy, or you see dipole moment times electric field then into cos 0 minus cos 45 degrees. So that is the energy that you have there. I just hope we don't get it confusing. Yes, so that is the energy, and you know that energy is the same thing with work done. So that is work is equals to this. So that means that I'll simply have, we've already gotten the dipole moment to be 1.505. Yes, So we've already gotten it to be 1.505 times 10. So we've already gotten it to be 1.505 times 10 raised to power minus 26, all into cos 0 is 1 minus cos 45 should be root 2 over 2, if you remember very well. That is cos 45, and that will give you the same thing as 0.707. Notice that apart from 90, once you are doing cos anything or cos apart from 90 and 270, cos of anything will be less than 1. So maximum is always 1, others are lesser. So I hope you will go and watch my trigonometry class so you understand what I'm saying. So by the time I now do, this will be approximately, by the time you now do 1 minus 0.7071, you get 0.2929. So times, so whenever they tell you energy, you know energy and work done is the same thing. I've proved it, joules. I've proved it in my physics class. Can check my physics class on work and energy. So if I know this, I can now times. Some people, what some students will want to do is to say, because they give them 45, P equals 45. P equals 45. It's not bad, but the only thing is that you need to always think of it in terms of, once they tell you that it is moving from equilibrium position to another position, always consider the initial angle minus the final angle. Yes, or yes, I think it's best that way. So you always consider, yes, the initial angle minus the final angle. Initial angle minus final angle. Yes. So I think that's the best way to put it. So theta 1 minus theta 2. So 1 minus theta 2. I'm trying to manage space. So this is going to be the same thing as saying 1.505 times 10 raised to power minus 26 times 0.2929. It will give you work equals to 4.4081 times 10 raised to power minus 27, or you see work approximately 4.4 times 10 raised to power minus 27 joules. And you need to know something. If you don't want to do this thing this way, if you don't want to do this way, you can say that torque naturally will be equals to PE sine theta, an integral of that. So by the time you now do that, you now come and do integral sine 0. Okay, sorry, what am I doing? So integral change in sine theta, sorry, I see 0 instead of theta. So this is going to be giving you C equals to PE cos theta. So I know it will take me doing a lot of calculus to explain this to you. You can check my channel on class on that calculus. But I want you to always remember what I've taught you. Overlook this. See it in textbook most times. Overlook it. So what you always need to think of is simply, at maximum torque, you have dipole moment times potential energy sine theta. Then at equilibrium, or yes, when they tell you equilibrium, at equilibrium, or they tell you to find energy, that is work done, will be equals to dipole moment times potential times energy, then cos angle, that is cos of yes, cos of initial angle minus final angle. So you need to just take note of these two. Less. That's the case where they did not give you charge, but assuming they give you charge and all those things, you now remember that this one is Q 2R. I'm using this 2R because of a case where they give you maybe a distance here, You remember to multiply the two together than using it separately. But if they call it a distance or totally, you can just use that particular distance for separation. Yes. So now if you know this, then this one. It's still the same thing with this. So initial minus final. So remember, yes, initial minus final. So remember that we normally do initial minus final, that is from the angle to the next angle. All right, less.